And a graphics processor is a specialist processor that is designed to make processing of three-dimensional images more efficient than other forms of processor. It is a digital world. It's all ones and zeros, adds and minuses. And if you do lots of adds, you can turn it into a multiply. But actually, a graphics processor takes a very specialist workload and does it much more efficiently.
What are the fundamental differences between a central processing unit and a graphics processing unit?
Well, fundamentally, we're here to put pixels on screens. So at the end of the day, we are here to execute some commands whose purpose is to say that pixel on that screen is that color. And usually that's presented to us as, here's some data. So usually there's a three-dimensional model. So in front of us is a table. There's a circle, which is a few feet off the ground, and it's X thickness, and it's got some legs, and it's at this position. There's some chairs in the room, there's me, there's the walls all around. There's a three-dimensional model. So first of all, you get given a bunch of coordinates and say the following things are at the following places. And then you say, given some more data, which is the chairs are lilac and the tables are sort of sludgy grey and such like. And so you get given some colour information, which is what we call textures. The geometry of the scene is usually broken up into triangles, because triangles is nice and simple. We're very simple people. We can't cope with complicated stuff. A triangle, 3 points, always has to be flat. You've never seen a triangle that isn't flat. And so you divide complex surfaces up into triangles, and then you have some information about what colour those triangles are. So you say, right, okay, I've got the geometry, I've got the colour. What do we do next? Well, you put some lights in the scene. So there's some lights in the ceiling which are shedding some light in certain directions. And then you need a camera. So you say the camera is here. So now you have to do some three-dimensional geometry to say, well, what does it look like in the camera? And the first thing you observe is, well, about half the room you can't see. Phew, that's good. So I don't have to calculate everything that's behind you. So the only things I have to calculate are the bits you can see, and you project it so that it goes onto a two-dimensional screen, and this is what it looks like. And then you move the camera around usually to get a sort of a real impression of moving through the scene. So there's a lot of different types of calculation involved in that. The first is loads and loads and loads of three-dimensional matrix arithmetic. You know, X, Y, Z coordinates, sometimes four-dimensional arrays with X, Y, Z and transparency information, and lots of RGB, red, green, blue, colour. So a device that's really, really good at matrix arithmetic is a good start. Floating point, because the positions of all of these things are usually expressed as floating point. And then finally, you've got this unit at the back which says, oh, well, I've got lots and lots of pixels to deal with, so we need to run through that and get them all into a buffer in memory. So some of that's really quite different from a CPU. A lot of three-dimensional plane equations have to be solved. So for example, here's the table, here's the floor. Well, which bits of the floor and which bits of this table can I see? So you have to do a lot of matrix solving to work that one out. And that's the difference in the problem that gets given to us, right? The difference in the design is we say, well, actually, I can do loads of this in parallel because actually I can do a lot of these calculations in parallel because they don't depend on each other. So every time you hear the phrase, for every vertex in the geometry do blah, for every pixel in the screen do foo, you can actually say, well, actually, that's a million pixels. I can actually calculate them in batches of 256 or something like that. So we extract the parallelism out of the algorithm and we design a processor that is actually very good at parallel processing. So the difference between a CPU and a GPU predominantly is, yes, there's some really, really fixed function blocks which we do very, very efficiently compared to a CPU, which does everything in software. But also, we are very, very good at extracting parallelism. So if I want to multiply three floating point numbers together, I'll do it more slowly than a CPU. But if you ask me to multiply 1,000,000 three floating point numbers together, then the length of time it takes me to do 1,000,000 will be a lot shorter than the time it takes a CPU to do 1,000,000. So we don't care so much about how long anything individually takes. What we work on is the bulk throughput, and it's a different end of the problem. And of course, there are blurred areas. And some people are now saying, well, actually, there's some sort of computing I could do that would do better on a GPU than on a CPU. And so you get this whole thing called GPU computing coming along, where people are not actually doing graphics, but they're doing throughput computing. And actually, that's been quite an interesting area.
Because I think one of the ones that somebody suggested was people doing Bitcoin mining with GPUs because it's just lots and lots of maths.
Yes, yeah. But also image processing. So in modern devices, you tend to have quite a poor lens, quite a poor sensor, and you're trying to take pictures that are as good as that camera you're holding in your hand that cost thousands. And actually that takes an awful lot of image cleanup. So there's an awful lot of computing that's taking place on those digital images. And it turns out that actually a lot of those go quite well when executed on GPUs, not executed on CPUs.
Can it fix my bad focusing as well?
That is coming. That is coming.
So what have we done? We've taken our local representation, moved it into world space, constructed a scheme.
So if you want to say 1/10 in decimal, you say 0.
And a new hash is found about every 10 minutes. So what happens is that hundreds of people